Welcome to the course on Power Electronics with Wide Bandgap Devices. Today I am going to discuss about Wide Bandgap Devices applications, which is considering reliability analysis part. So basically, whenever we consider any application, let's say integrated motor drives, renewable energy source applications, which I have discussed earlier, right? So there, before going into the application part, we need to do the reliability analysis of the converter. So why this reliability study is important? Basically, there are benefits of reliability analysis which are given as competitive advantages. What is the benefit of using any particular system over existing system? So that benefit, obviously from converter point of view, there will be some advantages, but whether the system will be reliable or not, so that can be concluded from the reliability analysis part. Then the systematic design of a product. So how the product should be designed, what approach we need to use for any new system, what are the modifications we need to do, what should be the method we can apply in any system. So that kind of design approach can be evaluated through this reliability analysis. Then warranty cost reduction. So if we are going for a new system, obviously there must be advantages with respect to economical point of view, which will give us the benefit in terms of cost. As I have discussed with you earlier, like these wide bandgap devices, from device point of view, they are very expensive as compared to the silicon devices, because of the manufacturing level is not as per the silicon devices. So that's why we have to consider the overall system cost. So we found that the overall system cost will reduce down as compared to the existing silicon device, because there are like additional requirement for silicon devices which may not be that significant in case of wide bandgap devices. So that is why the cost reduction will be there. And obviously whenever we say cost reduction, that we have to see for like throughout, like how much time we can provide this solution is for. So basically how many years it can operate properly, so that kind of thing will be there. And then obviously customer satisfaction will depend upon if the system operates properly for long time. So these are the advantages of reliability study. So that is why we need to consider reliability analysis. So I'll just give you brief idea about this reliability study, how it can be done for any new system, so that you can use for any new device whenever it will be applied to any application, so considering like power converter. Okay, this need for reliability study, anyway, like I told you, so these are the advantages. So but why we need this? So we need to find out the stresses. What kind of stresses we generally see in power converter? So generally we see this temperature stress, which actually comes from the power losses. So basically, when I have shown you the analysis of the power converter, how the temperature can rise. So basically from like temperature calculation part, where exactly I have shown you that the heat sink design part. So there you have seen that from power loss we can directly calculate the temperature which will arise in that particular device or the system. Now when you have the temperature, so then what you need to do, then you can easily find out the type of heat sink will be suitable to take out the heat from the system. If in case we cannot do that, we fail to do that kind of operation, then there will be stress in the device. Stress means temperature can change the property of the device, that you have already seen. So like if we cannot take out the heat, then it will change the property of the device. Eventually it will increase further heat, and then what will happen? Then it will ultimately destroy the system. So that is why we need to have idea about the temperature, how much it is actually generating in the device itself. So this temperature stress we need to find out. So second thing is the environmental stress. What are the environmental stress? Obviously there is like environmental effect in terms of temperature, but there are other effect also, like if the system is placed in a steady location where only temperature is the part we need to consider, or in addition to temperature there can be vibration effect also. So let's say if the system, so if we consider electric vehicle kind of applications, so where there what happens, the converter will be placed in a vehicle or the car, so basically their car will be in the moving condition. So then along with temperature there will be other factor which will also affect the device which will be placed in the converter, or maybe if it is placed in the more aircraft application. So then what will happen, then it is like in space application or plane or anywhere, so there will be vibration effect also for that. So this will come under environmental stress. Okay, so this stress if find out, so then what we have to do, we have to see how much time the system will operate properly in a given environmental condition, temperature, high vibration, everything. So then we have to find out what are the factors that is going to get affected in the device, so that will give us the failure rate. Okay, so then once we have the failure rate, we can actually provide warranty for that much period, whatever failure time we will be able to get. And then we can also find out ways to improve the reliability. So let's say if any system is placed in any particular application, let's say motor drives or maybe renewable energy, so then based on the application there can be different control methodology, algorithm, those we need to use. Then if any method is not suitable, or maybe that can cause failure much higher rate than the any other method, then we can actually provide suitable method. We can for that we have to find out what are the failure rate and all this thing, and also we can provide algorithm so that it can give us some benefits over existing kind of algorithm. So this is important for development or manufacturing of any system related to wide bandgap devices. So this is what is essential for industrial development. So until and unless they provide warranty of the system, they will not be able to use this for industrial application. So this is why it is very important. So how do we get this lifetime model? So there are various lifetime model which are existing for silicon based system. So you can see this Coffin-Manson model, Coffin-Manson Arrhenius, barrier. So all these models are there. So what we need to find out? Then minus damage accumulation we need to find out. So this accumulation rule give us, so you can see summation of I to n in small n I divided by capital N Fi. So capital N gives different temperature, with respect to that what will be the damage accumulation. So N1, N2, N3 are the damage accumulation with respect to different temperature. And as each cycle is completing, let's say the system is running for few times, like it is actually operating for few cycle initially, then the temperature may be different, and with respect to that the damage accumulation can be calculated. Now as the temperature changes, then again the damage accumulation will be calculated. After some time the temperature may change due to environment or maybe due to stress of the devices. So anything can cause change in the temperature. So then the damage accumulation with respect to the other temperature will be different. So by adding all the temperature and the damage accumulation, when it will become addition, summation of all this parameter will become equal to 1, then the device will be completely damaged. So means the damage accumulation is reached to the maximum level, so device cannot operate in that time. So these are the methods which we need to use in order to find out like how long the system can operate. Then only we can give us that okay fine, this much time it will operate properly. After that you have to basically check the condition of the device or the system, and then you need to like replace it or maybe repair it, so whatever will be suitable. Okay, so now if we have to use this in a power converter, then what we need to do? So this is a simple boost converter. Anyway, like I have discussed about boost converter simulation and then PCB design. So now we are going to see this simple boost converter analysis with respect to the reliability part, to see that what are the parameters we need to consider. So you can see this boost converter, obviously it is having this input voltage source, then input inductor, switch, diode, capacitor, and then output load. Load is shown here as the resistance, and voltage across the resistance is shown here as V0. So then the reliability in this case is evaluated by considering MIL HDVK handbook 217F. So okay, so this handbook provides the reliability analysis part, but that is by considering the silicon devices. Obviously wide bandgap device is much different than that of the silicon device. There are some differences there. So then what we need to do, we need to check the failure rate of each component. So here they have considered the failure rate of each component are constant. So then each component means you can see here this capacitor, inductor or transformer, like basically magnetic component they are considering, then diode and the switches. So these are the formulas for the failure rate. Now these formulas are directly taken from the handbook. If you want to know more details about this particular different component in this formula, so you can actually refer this handbook. So there are actually different components are like quality factor, so like environmental factor, then failure of the devices, they are related to different parameters. So this you can see here. So now this is like considering the exponential distribution if t equals to epsilon e to the power minus epsilon t, rt equals to the power minus epsilon t. Now this will give us basically ultimately getting failure rate of each component will give us what will be the years or failures. So basically year of failure for this particular system considering different ambient temperature. As you can see here, so like this, as the frequency is increasing, so as you can see here, so the failure rate it is actually much higher, means the years it will be able to sustain properly, that is actually much less than that of the operation at lower frequency. So this is very much important because as we are considering wide bandgap devices, obviously we are actually looking for high frequency operation. So here the frequency ranges are shown from 10 kilohertz to 100 kilohertz. So 10, 20, 30, 40, 50, 60, 70, 80, 90. 100. So you can see here, so there are different lines are shown. So the 10 is the line which is the topmost line, so which is giving here as the temperature increases, obviously failure rate it is increasing. But any particular temperature if you consider, let's say 30 degrees Celsius, so 10 kilohertz number of years it will be able to sustain, it is more than 9. And when we are considering as 100 kilohertz, then number of years it will able to sustain, it is around 6.5 years. So that is how much it is shown here. So as we are actually considering this high frequency operation, obviously the failure rate will increase. Then what we need to do, we have to find a way so that we can maintain the failure rate, means let's say it is 9 years and it is 6 years. So instead of 6 years, how to improve the failure rate to 9 years even at 100 kilohertz operation, that is the part our role comes. So probably we can provide methods or maybe different like design for the power electronic converter, or we can evaluate like how this temperature effect stress, environment stress can be less, can affect the system less. So those are the ways we need to find out and implement for any new device based system, so that we can maintain at least the years of failure to the previously existing system without obviously the other advantages should come here. So but like we should not affect the failure part. Okay. So, in terms of reliability analysis, what are the shortcomings given in the handbook? So, basically, the handbook which is given for the silicon-based devices, so there, the shortcomings are the failure rate is constant throughout its useful life period. Means this failure rate, it may not be constant, but the failure rate doesn't remain constant over time. So, that is the part we need to include in the given method, or maybe for the new devices. The reliability analysis is done by considering zero interaction between the components. So components, they interact with each other, means there will be different parasitic components. So how to include the parasitic component for failure analysis, that part we need to look into. Only the mean junction temperature is considered for switches during calculation of the failure rate. But junction temperature swing also affects the MTTF of the switch. So that we need to consider. The failure rate data of IGBT isn't available in this handbook, and hence a WBG device we need to consider. We need to provide new method using WBG devices. The driving cycle of the converter isn't taken into consideration. That we have to consider what will be the different stress, because as the driving cycle changes, stress in the devices will change, and that is going to affect again the failure rate. So this driving cycle plays an important role in finding the reliability of the product. Okay, so these are the things we need to consider, which is not given in the handbook, existing handbook. Okay, so you can see here, so this is one example is given. So how this environmental factor will change and the power level will change, will affect the failure rate. So you can see the left hand side, the first waveform which is shown here. So it is with respect to the first one is the with respect to fixed environment, second one portable environment, like for EV applications, so where you can carry it. Then third one is the rotary craft, so particularly aircraft application. So you can see here, as the fixed environment, you can see the number of years it will be able to sustain is much higher than that of the rotary craft. So comparison of lifetime of converter operated at rated power under different environmental condition. Okay, so this is the part which is shown here. So the vibration also affects the time of failure of the converter significantly. This MTT wave obviously can be improved by properly selecting power level, frequency and cooling. So you can see here this right side waveform is with respect to the different power level. So here they are operating at rated power, so this is blue one. Operated at 50% rated power, then orange one it is much higher. Rated power with improved cooling, so it is actually gray one. Okay, so you can see here, so low power level it will be able to operate much higher, means failure rate will be less. And in the whenever it is having rated power, then what will happen? So then this number of failures will be much higher, then years of sustain will be less. So here comes the driving cycle part. Whenever the driving cycle we have, so that time we will have the information about the system power level, whether the system is operating at rated power or half of the rated power, 10%, 20% of the rated power. So then that way the failure rate will change until and unless we have the driving cycle. So we'll not be able to comment properly on the reliability part. Maybe if we have the driving cycle, let's take an example. So if we consider the reliability of the system considering the rated power condition, maybe it will be able to sustain for 5 years. Now if we consider the system using half rated power, then it will be able to sustain for 15 years. Now our system, if we have driving cycle, maybe sometime it is operating in half power system, half power level, sometime it is operating at full power level. Maybe if we have the information of the driving cycle, then we will be able to get the reliability as 10 years. So until and unless we include the driving cycle, we cannot really comment on the reliability. either will come in 5 years or 15 years, both are wrong, right? So that is why it is very important to include driving cycle, and that is where the application part come, and that is where the power converter part come. So power converter we need to fix first, then where exactly we'll be applying it. So these two parts are very important for studying the device in actual application. So there comes the actual application related reliability analysis. So this is very much essential for industrial application or industrial design, or maybe using the system for like any like product. So this is very important part. So this is considering lifetime by particular driving cycle. So you can see here, so this is maybe, let's say this is the driving cycle of the converter topology. Initially for T1 period, so the power level is increasing. So for T2 it is fixed, and T3 it is again decreasing. So there are three phases you can see here. So it is actually divided into phase 1, phase 2 and phase 3. So three phases are divided, and now based on the three phases, again this voltage acceleration factor you can see here, it is given in the equation. This is from the handbook AFB. So e to the power beta V stress minus V operating. So this is actually calculated accelerating factor, and then similarly voltage accelerating factor we have the temperature accelerating factor. So this can be calculated by using e to the power EA by K 1 by T operating minus T stress. So EA is the activation energy, which is given as 1.82 eV. K is the Boltzmann constant, which is 8.617 into 10 to the power minus 5 eV per Kelvin. And V stress is taken here as 650 volts, and T stress is taken here as 150 volts. So stress means this is the maximum. V stress is the maximum voltage, and T stress it is maximum temperature. Okay, then based on the operating temperature, obviously this accelerating factor will change. Then again the operating factor temperature depends upon the converter driving cycle. So based on this, like this temperature accelerating factor and voltage accelerating factor, we can actually check converter power loss by using converter power loss model. Again, for converter power loss we need to have the information of the converter prototype itself. Once converter power loss model we have, from there we can get the thermal model. So you can see for phase 1, phase 2, phase 3 it is same. Converter power loss model, and from there we are getting the thermal model, and thermal model we are getting the temperature accelerating factor, and obviously for phase 1 also like voltage accelerating factor we will get separately, and temperature accelerating factor, voltage accelerating factor we are like here we are multiplying with the T1 by mission time, and then summation will give us the basically total reliability or total time it will be able to sustain. Okay. Now this is the whole system. So basically we need to have idea about the mathematical model and the experimental data. Then only we can comment on the system reliability, right? So we have to fix the power converters. Let's say this is one converter. It is fixed. Then from here, for each power converter, the power loss model will be different. We need to get the power loss model. And then from power loss model we need to get the thermal model. So anyway, this Foster and Cosas model I have already discussed with you long back. So there you can refer that, and then by using the rain flow count algorithm, cycling like how many cycles we can get, so that we can count. So this can be given here as TJ mean. So now calculating time required, increase this like 8 to 10% RDS on, and find present efficiency by putting RDS on in efficiency time. This we can actually use in the final result for calculating lifetime of switch and capacitor and efficiency and the usage time. So these are the total thing we have to do in order to find out reliability of the system using any device or from the device perspective, right? So thank you. That is all for today. So yeah, so this is all about this particular course. So I hope this is beneficial for you, and you can use this device by referring this particular course. You will be able to use this device for development of any product or any system which will be useful in industry. Okay, thank you very much. Thank you.